Okay, quotient rule. So you need to remember what the quotient rule is. He will not give it to you. You won't get any formulas in this class, basically. Don't forget it. All right. So the quotient rule is when two functions are being divided by one another. So it says, and the order matters when you're doing the quotient rule, okay? So it says you have to do the derivative of the top function, which will be f prime of x, times the bottom function, which is g of x, minus, product rule was addition, quotient rule is subtraction, the derivative of the bottom, which is g primed, times the top over the bottom function squared. Okay. Sorry, what's the mi high d low thing? No, you don't have to start with G. You don't. You're telling me it matters if you go 2 times 3 or 3 times 2? Yeah, I don't remember that. I hate that thing. I hate it. Just remember the formula. No, he does not. Somebody told it. I was in the class. Somebody told it to him like 2 years ago or 3 years ago, and now he says it. He never uses it. No, what is it? I don't even know how it goes. Low, mi, high. Low, D high. Low, bottom times the D high. Derivative high. This is so stupid. Me minus.
That would be D high low.
Whatever the formula is, I don't know what it is. Okay, let's just do a derivative. So. There we go. Okay. So, what do I do? Derivative of what? Didn't use the song. I am not using the song. Derivative of what? Top or bottom? Which is 5 times the bottom function minus derivative of the bottom, which is 2x times the top function over bottom function squared, right? So don't expand out the bottom, just write it x squared plus 2 all squared. Don't expand it out. Do not cancel the x squared plus 1s, all right? Simplify the top, all right? Expand the top, get rid of the brackets, and collect your like terms. So we'll get 5x squared 10 squared. And that's it. Just leave it like that. Okay. Is that okay? All right. What if we have do one with a trig? Derivative of sine x over x cubed. That is cubed, x cubed. People get that? Can you simplify that anymore? You can take out an x squared from the top. And then cancel that, and that would become 4. So your final answer would be x cos x over x to the 4. Sorry? Yeah, that's why I went from x to the 6 down to x to the 4. This one? Oh no, I crossed out the 6 because these two x's will cancel 2 of those and become 4. So I just wrote it there. Actually, I'll do that. Now, Torsten didn't show you this, but you don't actually have to use quotient rule ever if you don't really want to. It makes your life easier, but this particular function, I could rewrite this as a product rule. Anybody know how I could do that? Yeah, so flip the x cubed up, essentially, right? So you can think of it as this way. That. And that's product rule, right? So we should get the same answer. So product rule would say the derivative of the first one, negative 3x squared. Oh, sorry, not negative 3x squared. Take away 1, so negative 4 times the first function plus the derivative of sine is cosine. Which really means we have this. Do those look the same? Well, they are the same, but you just have to put them together, right? So if you're going to make a common denominator, you'd multiply this one x and x, which would then give you which is the same as that. Okay? It doesn't matter which one you use. Okay? Sometimes it's easier to use quotient rule, but you can always make it a product rule question if you want to just flip it up and make the exponent negative. And I got one more to do before I give you some practice stuff. And then we'll do higher order and we'll do chain. We'll start chain rule today because he's going to do that tomorrow. So you get an introduction of what chain rule will be. All right. All right. What if I have this? Before you do anything, what rule do you want to use on this one? You can use quotient rule. It's not going to be wrong, but quotient rule is obviously more complicated, right? What do you notice about the denominator? It's a constant. What are you allowed to do to constants? You can't kill them, but you can pull them outside of the derivative, right? It doesn't have it up here, but essentially you can pull the 1/6 outside and then just do the derivative of that, which is a simple polynomial. So what's the derivative of x squared plus 3x? 2x plus 3. So your answer would just be 1/6 times 2x plus 3. Multiply that back in and get 1/3 x plus half. So if there's constants, especially in the denominator like this, sometimes it makes sense to pull them out because then you can do it in one step, basically. All right. Along those same lines, if you have something that has a denominator that's not a constant, but if it is a single denominator, like this, what do you want to do here? We could do quotient rule. We could flip the x up, make it negative, do product rule. You can't pull a variable out. You can only pull constants out. But what you can do, if you have a single denominator like this, is rewrite it Is that the same thing? Okay, simplify that. X squared over x is just x. 3x over x is just 3. So really, that's the derivative you're doing. Sorry? What's the answer? 1. Okay? So simplify things first if you can, because it'll make your life way easier. So if you're going to do quotient rule, that's going to get, it's not going to get super ugly, but it's going to get big before it simplifies down. Everything will just cancel in the quotient rule, but this is way easier to do. Okay? All right. If you want to remember me high, D low, me low, low, high thing, go for it. I will not do that. Here's your questions. Page 125, numeros 7 to 11. These are all odds that you're doing. 7 to 11. Ooh, 37 is a good one. 37, it is. I think so. Did anybody do my review from the Okay, good. So you can do 65 then. No, you should probably look at it then. 73 you can do. Yeah, there you go. All right. There's your questions. Where's my... All right. Derivatives do not exist in 4 specific places. All right. Number 1, vertical asymptotes. Which makes sense if you think about it. So, vertical asymptote. So if I have a graph that looks like this, boom, 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 boom. Let's call it 4. No derivative will exist at x equals 4. If I call this f prime of f of x, f prime of 4 dne does not exist because there's no point there, right? If the point doesn't exist, you can't draw a tangent line on a point that doesn't exist. Okay? So vertical asymptotes have no derivative. The derivative exists everywhere else on that function except at x equals 4. So if you take that, can you think of another one where a derivative wouldn't exist? Sorry? A pod or a jump, both of those. So we'll do pods first. I'll even write it as a pod. Point of discontinuity, or a hole, or an undefined point, whatever you want to call it. So if you have a graph with a hole in it, I'm going to put C for constant because I don't like putting specific numbers. So f prime of C does not exist because you have there's no point there. So you can't draw a tangent line. Just if you think of it that way, that you cannot draw a tangent line, it makes sense. Third one is vertical tangent lines. So who's taking Chem 12? Perfect. What does this graph remind you of? Yeah, titration. So if I was talking about pH, this would be like a buffer type thing, right? Remember buffer curves? Chem 11? Okay, but buffers and things like that, pH curves, right? This has a vertical tangent line right through that point. What's the slope of a vertical tangent line? What's the slope of a vertical line? Undefined or infinity, right? So, and what does the derivative represent? The slope. And the derivative is actually, Torsten did it right at the beginning of class today. It's actually what from the first bit? You never use it this way, but it's a limit, right? Right?
Yes. Oh my God.
So if the limit is equal to infinity, that means the limit doesn't exist, which means the derivative doesn't exist. Okay? So if I call that C, again, f prime of C equals dne. I'm going to put infinity, but it's not infinity. You just say it doesn't exist. Okay? But if you think of it as a limit, it makes a little more sense. And then the last one isn't as intuitive, but you just have to know. Sorry. Sorry, Oscar. Sharp turns. Not shark, sharp. So the infamous, the one that you've seen before would be an absolute value graph like this. Okay. The derivative at C does not exist. And again, if we go back to it, the derivative is actually a limit, right? And if you did the limit, you don't have to write this limit bit down. You just have to know where they don't exist, okay? If you did the limit as x goes to c from the right and the left-hand side, it's of f prime of c. The limit of the derivative from the right and the left side. So essentially, it's saying, what's the slope of this line here? I could say that's 1. Sorry, this would be 1. And from the other side, it'd be -1. Because the derivative limits don't match from either side, it doesn't exist. All you need to remember, okay, you don't need to remember this bit. All you need to remember is when you have a sharp turn like this, not a curve, but a sharp turn, the derivative at that point does not exist.
How do we know that without looking at a graph, or will it be put in a question?
It would be in a graph, or you'll see when we do curve sketching tomorrow, we're going to learn about critical numbers, and they kind of just pop out. Like, it'll be obvious. Okay?
But that's not like an absolute value.
No, we don't do derivatives of absolute values in this course. I could give you the graph of it and say, where does a derivative not exist? But I wouldn't give you the equation and say, find the derivative of it. And so sharp turns also, and these ones you will see things like this. So graphs that look like that, where they have this sort of peak. This is called a cusp. Okay. The derivative does not occur there either, because that is a sharp turn. It's essentially when the graph is not a gradual turn, it's just immediately it goes from being a positive slope here on this side to a negative slope on that side. All right, it happens instantaneously. And just if you're interested, cusps usually occur, well, not usually, they do occur, when you have fractional exponents. So things like x to the 2/3. That has a fractional exponent. But we'll talk more about that when we get into curve sketching, which will start tomorrow, okay? So you just have to know when derivatives don't occur when I give you a graph, or when Torsten gives you a graph. So if we look at, shrink down, there we go. This graph right here, tell me, where does the derivative not exist? Okay, so -1, f prime doesn't exist there, right? Because that's a hole in the graph. It doesn't matter that it has a value down here. Irrelevant, hole in the graph. Where else did you say? 2, all right, because it's a jump, all right? Okay, so f prime of -1 does not exist. F prime of 2 does not exist. If I said, and this was on the question from the homework I gave you, if I said, what is f prime of 3? What is it? -1, right? Because the derivative is the slope. The slope at 3 is right here. It's a straight line. You're just doing your grade 10 rise over run. All right? Rise over run, which is down 1 over 1. So it's just -1. Okay. We okay with that? All right. Now we're going to do higher order derivatives, which are super fast. So
Bay. It's me, Hillary.
And me, Dominic, for your daily announcements.
So if I have, remember math, physics 11, when you would do, I think we talked about this before, you do that ticker tape thing, and then you, with the car down the slope, and you'd measure the dots. Did anybody take COVID physics? So you didn't do any of that stuff. Oh, you did it? Okay. So if you did it first semester, you would have done it. Okay. Anyway, you would do a graph of position versus time, and then everybody would draw a tangent line, and you would, it's not very accurate, you do rise over the run, right? It's not accurate at all. But I don't care that it's not accurate right now. If you draw the tangent line and we do rise over the run, the rise is in what units? Meters. The run is in, so it's meters per second, which represents the velocity. And the slope of the tangent line in calculus is represented by the derivative. Therefore, the first derivative is the function. There you go. Yes. So the first derivative represents the velocity function. Okay? It's meters per second. If you did it again, so I'm not going to draw the graph, but if you sketch the graph of velocity versus, you know what? Let's just do it. So, and then I'll summarize it. So if I have, because it's a little more complicated. All right, so then if you do a velocity, this is velocity. A velocity time graph, how fast it's moving at each certain amount of time. I'm just gonna, I don't know, whatever curve will be like that, say. And we did a tangent line on that. Boom. Tangent line slope is going to be rise over run. What are the units for the rise? No, look at the graph. Meters per second, right? What is the unit for the run? Time, or seconds. So this is meters over seconds divided by seconds, and everybody loves fractions. What do you do when you're dividing fractions? Flip the bottom and multiply. Which gives you meters per second squared, which is the, so the second derivative represents the acceleration. Okay? This is physics and it gets used all the time. Sorry? Can't hear you. So, oh, this is, yeah, it's going to lead into that. So the first derivative equals velocity. Second derivative equals acceleration. The one thing is you have to have the function to do these things, right? In physics 11, you didn't have the function. Although you probably could have figured it out. So it was usually just a parabola or something. But second derivative is the acceleration. If you did the third derivative, it's called the jerk. It's how fast you are accelerating. It's the acceleration of your acceleration, essentially. And then, look, you don't have to remember these. You're not going to be asked them. You're going to be asked velocity and acceleration. In this class, you won't be asked the other stuff. And then the fourth derivative is the snap. The fifth derivative is the crackle. And the sixth derivative is the pop. So go snap, crackle, pop. Because engineers / physicists thought they were funny. That's not what they're called. Like that, those aren't formal names. They actually don't have formal names. But a lot of people just use those interchangeably. A friend of mine's an engineer. He uses the jerk because he's a software engineer, and they make programs for machines that make parts for other machines, but they're really, they have to be really precise down to the, I want to say the angstrom. Do you guys know what an angstrom is? Oh my gosh. Okay, 10 to the minus, an angstrom I think is 10 to the minus 6 or 9, I can't remember. Doesn't matter. Anyway, 10 to the minus 6, like 6 decimal places, all right? That's how accurate they have to be. So if the machine accelerates too fast, it'll move the table. You won't see the table move, but when you're trying to be that precise, it will mess up the result, okay? So they say that their machines have a jerk limit. Do with that what you may. All right, so notation, it was in Torsen's thing, f prime is the first derivative. Second derivative is f double prime, you just put 2 primes. After that, they tend to just put the number. So you can do for the third derivative, you can say 3 primes, but they'd probably just say that. And then f4, f5, f6, all the way up. You can do it an infinite amount of times, okay? So the standard question that you would get would be something like, a particle has a position function described by, let's do a parabola, x squared plus 3x plus 1. And it shouldn't be x's, it should be t's because we're doing t's. T squared plus 3t plus 1. And I say, how fast is the particle moving at, we'll just make it simple, t is equal to 1. And what is his acceleration? That time. So basically, at 1 second, how fast is the particle moving, and what is the particle's acceleration? So if we're in the derivative unit, what is the very first thing you do? Derive it. Sorry, differentiate it. F prime of t, what's the first derivative? 2t plus 3, which is the velocity function. So how fast is it moving at 1 second? 5, right? Just plug in t is equal to 1. And if we're in, I should have said we're in meters and seconds, so we'll just say meters per second. So at 1 second, it's moving at 5 meters per second. How fast would it be moving at 2 seconds? 7, right? Put in 2. If I said 5 seconds, put in 5. That's all you do, okay? If I want to know the acceleration of the particle, take the second derivative, which means you take the derivative of your first derivative, right? You just do it again. So what's the second derivative? It's just 2. So what's the acceleration? 2 meters per second squared. Which means it has a constant acceleration. Acceleration doesn't change. No, you just have to keep doing it. You just have to keep doing it. Unless there's a pattern like the trig one, like the sine and the cosine that cycle back every 4. But if it's a polynomial, you just have to keep doing it. And it could be if it was a quotient, it would get really big, which would be, I'm not going to give you one of those, and he won't give you one of those either. Okay? Is that okay? Oh, sorry. Yeah. You just plug, when you do that, you just put in, if I say, what's the acceleration at 1, you just put the 1 in to that. If it was a cubic function, it would still have a variable in it. Okay? All I want you to do is, what do I want you to do? Page 127, numbers 91 to 97, please. The one that I just wrote up? Yeah, you'll probably have something similar like that. But again, on... All right. And this will be part 1, 2.4 in your book. So there's 2 parts to the chain rule. This is part 1 today. Torsten will introduce it tomorrow. I'll do my part 2 tomorrow, okay? So far, you've seen functions like this. X squared plus 1. That's pretty straightforward. What is the answer to that? For the derivative, sorry. 2x. All right? Y prime would be 2x. Not too bad. You could even do, if I said y is equal to x squared plus 1 all squared. You could even do that. How would you do that? What? So you would, yeah, you could either write them both separately. You could write them like this, right? We're just using the rules we know right now. That's okay. So you do that, use product rule, or you could multiply them together and get x to the 4 plus 2x squared plus 1, and then derive that. Okay? Those are the only ways you know how to do it right now. So your y prime would be 4x cubed plus 4x. Okay? But if I said, do this, that to the 10th power, you're not going to write out x squared plus 1 10 times and either multiply it all together or use product rule on 10 functions. It's going to be massive. All right? So when you get something like this where you have a function inside, now I'm going to start saying the inside function and the outside function. Okay? The inside function, Torsten's probably going to use slightly different language. So this is the inside function. This is the outside. Okay, the outside function. All right. Inside makes sense. It's inside the brackets. The outside function is the power of 10. Okay. When you get a function like this, you use chain rule. Okay. When you have big exponents, chain rule is your friend. Okay. I'm gonna use what I call the general power rule. It's just a version of the chain rule. Okay. So general power rule. Which, here's our power rule here, x to the n. General power rule says if I have some function u to the power of n, then my derivative will be, follow this. We drop down the n. You take 1 away from that exponent, so u to the n minus 1. That's exactly like the stuff we did with the general power rule. The only difference now is, because our inside function isn't x or anything like that, it's a complex function, x squared plus 1, could be sine x, could be anything. You multiply by u primed, the derivative of the inside. So this bit is the outside derivative, and this is the inside. Oh, stop it. U is a function, like 3x plus 1, or sine x, or in this case, it would be x squared plus 1. Okay? So once you do a couple of these, it's pretty straightforward. So we're just going to practice them right now. All right. So if I have, you know what? We'll just use the function I wrote up there. X squared plus 1 to the power of 10. Jesus. Nobody wants to write this out 10 times. So if I ask for the derivative, drop the 10 down. So drop the 10 down. Everything on the inside stays the same. You take 1 away from the exponent, just like we did before. That's basically the power rule. The only difference is, because we have a bunch of junk inside there, the x squared plus 1, we have to multiply by the derivative of that. So then we just multiply by, what's the derivative of the inside? 2x. And then you can clean it up a bit. 2x times 10 is 20x. And that's it. That's it, you're done. That's all you do. That's the, I mean, look, they're going to get more complicated. Yeah. What? It's 1 better than 10, or it's 1 less than 10. No, I'm not asking for the this is the derivative. So if I said, if this was a, say, position function, not that this would ever be a position function, right? But say it was x squared plus 1 to the 10th power. And I said, that's the position function of a particle. What is the velocity of the particle? You would take the derivative, which is done right there, and then just plug in your number. Okay. This, then you're going to have to use product rule, because you have 2 functions, but it's actually a product plus chain rule. That's the next step. That's tomorrow. So we're not going to worry about that right now. Okay. All right. Let's do another one. B. Okay. There's our function. F of x is equal to 3x minus 2x squared to the power of 4. What is your first step? Drop the 4 down, right? Just take 1 away from the exponent, and then you just multiply what the derivative of the inside stuff is. I would just leave it like that. I mean, you could multiply the 4 into it if you wanted, but don't worry. Tomorrow, the simplification process is going to get a lot more complicated. So just embrace the fact that you can just leave it like right there. Embrace your intuition. So here's your last question of the day. Last question I'm going to do. 1 over x squared plus 1. So right away, this looks like a quotient, but you don't have to use quotient, right? So you can flip this up now and rewrite it like this. Like that, right? Which means now I can just use chain rule. Okay? What does chain rule say? Drop the -1 down. Okay. Times, you can use quotient rule if you want. Times the inside derivative. What's the inside derivative? 2x. And then the only thing I would do if you have a negative exponent, what do you do to make it positive? Flip it down. So really it's just -2x over. That's probably going to be faster than using the quotient rule. But maybe not. Okay? So chain rule says, take your exponent, drop it down, or general power rule. Drop it down, take 1 away from the exponent, and then multiply that by the inside derivative. And that's it. Okay? Page 136, 7 to 21, odd, please, plus any other questions you didn't do. I will do a summary at 10 after. Yes. Yeah. Okay, so summary of all the derivative rules we have. We have the general power rule, which is the first one up there. The derivative of x to the n is equal to n times x to the n minus 1. So the simple, straightforward one would be like x to the power of 4. All right, you drop the 4 down, take 1 away, you have 4x cubed. Then we did product rule. What is the product rule formula? Yeah, f prime. It's the derivative of one times the other times the derivative of the other one times the original. Whatever. Yeah. It's that, basically. F prime times g plus g prime times f. Okay? You would use that, obviously, when you have two functions being multiplied together. So if you get anything that looks like this, that's product rule. Okay? That's what we did before spring break. Then today you learned about quotient rule. What's quotient rule? No, me Heidi Lowe's. Just tell me what the quotient rule is. There you go. It's the derivative of the top times the bottom minus, quotient rule is always minus, subtraction, the derivative of the bottom times the top over, there you go, over the bottom squared. So that was stuff that looked like this. Just do really simple. So something where two functions are being divided. Yes. It's in the proof. You got to look at the proof to see it. I can show you it tomorrow if you want. Didn't Torsten put it up today? But probably went through it at Mach 10. Yeah. Okay. If you really want to see it, come see me tomorrow and I'll show you. Okay. It involves the limit definition of a derivative and all that stuff. You have access to the thingy. Don't know. All right. Then we did trig derivatives. So the derivative of the sine function is cosine function. And the derivative of the cosine function is negative sine. Okay. And the final rule that we learned was the chain slash general power rule, which basically says if you have something like that, this is the general, and I'll write out an example. It's n times u to the n minus 1, which is like the power rule, times the inside derivative, u primed. Now that's a general power rule. I'll write the chain rule. The chain rule says this. I'll do it in red. Chain rule says the derivative, because it's for composite functions. Remember Fogg and Goff from grade math 12? So when you have one function inside of another function, that's essentially what we had. It says f prime of g of x, the outside derivative times the inside derivative g prime of x. That's chain rule. Okay, so these are the same thing, these last two. They're just written slightly differently. And you use those when you have examples like this, when I ask you to do x squared plus, I don't know, 5x to the power of 7. Okay? So then you would use chain rule. Yes. The derivative d, so this top d means the derivative of the whatever this function is with respect to x. D over dx. You only have to write it until you're going to actually do the derivative. Yes, until you do it. So at like this point right here, I say d dx of this, but as soon as I actually do the derivative, I don't write it anymore. Okay. Yep. That they are because, but you have to, like for this, I would say if f of x is equal to sine of x, then f prime is equal to. Yeah, that's fine. Yeah. You're gonna see it mix and match all the time. Oh, and then we did, the only other thing we did was where derivatives don't exist. Okay, so no derivatives. One, I'm just gonna draw the pictures. VA, vertical asymptotes. Where else? Pods, holes. I should say or jumps too. So pods or jumps. There's two other ones. Vertical tangent lines. So it's like the buffer curve or the pH curve for titration. Thank you. Chirp turns. So we had the cusps, or you had the classic absolute value V shape. What's the first derivative represent in physics? Velocity. And second? Yeah, so second derivative equals the acceleration. All right, that's pretty much it for today.